Hello all of you. So, in the last lecture we have discussed the idea of thermodynamic functions. We discussed the idea of Legendre transformation, how can we get the energy functions that we know, internal energy, enthalpy, Helmholtz and Gibbs free energy. So, in today's lecture we will extend these ideas to multi-component systems, and we will also discuss why do we say that we should always have the minimum energy of a system, the minimum Gibbs energy or Helmholtz energy or whatever description that you may recall. So, what is the theoretical basis for that particular logic? So, just to quickly recap, so we have discussed these four functions: internal energy U, enthalpy H, Helmholtz free energy F and Gibbs free energy G, which are defined in this particular way. So, H is U plus PV, F is U minus Ts and G is U plus PV minus Ts, and we can also write this in differential form as du is Tds minus Pdv, and all of this is for a one component system. Df is equal to minus SDT minus Pdv and dg is minus SDT plus Vdp. So, naturally these guys are functions of different controlling variables. So, let us first discuss what exactly will change if I have a multi-component system. So, for doing that, let us first discuss like what exactly happens when we add a molecule to the system. So, going back to our example, when we were distributing quanta of energy into different molecules in the system, we always assumed that the number of molecules are constant. But let us say, for example, if I have a system containing some molecules n, and let us say, for example, if I want to add a new molecule in the system is going from n molecules to n plus 1 molecule. So, when that molecule moves in, let us call it a foreign molecule that moves in the system, that molecule must be carrying some energy where from it is coming from. So, let us say, for example, in a bulk system, let us say, for example, we mix two liquids, then molecules in one liquid will move to the other liquid. So, that molecule that is coming from one liquid to the other, that must be coming with some energy. Then once it comes here, then it forms new pairs or new forces with the other molecules already present in the system. So, let us say, for example, the new foreign molecule is liked by the molecules present in the system already. In that case, we say that the mixing is favored. If it is not liked, then the mixing is not favored. So, all of this must be coming in terms of some energetic condition, that in one case it should be favored and in one case it does not, that must be driven by some energetic condition, and that is where the idea of chemical potential comes handy. So, what a chemical potential essentially is the change in the energy, and we discuss like which energy we are talking about in a minute, but this is a change in the energy of the system by adding a molecule. Now, as such, the idea of chemical potential is also valid when you have the one component system, let us say for example, if I add a water molecule to a glass of water, so that water molecule must be carrying some energy as it comes in. However, provided that the properties of that water molecule is the same as all the other water molecules in the container, that change is simply adding to the volume of a system, right. We will discuss in the next lecture the idea of intensive and extensive variables, and there you will see that if I simply mix two pure liquids, we basically do not change the intensive variables, and we come to that as we go there. However, if I add a molecule of a different species than that is already present, or molecule of an species that is already present, but adding that molecule changes its concentration. Let us say if you have a binary system of A and B, and you have let us say 10 A molecules and 20 B molecules, by adding a new B, you are changing the ratio of A to B molecules. So, by addition of a molecule, you are changing the composition of the system. So, whenever that happens, this energy becomes non-trivial, and that is where the idea of chemical potential becomes more relevant. So, in general we define mu j as the change in energy by adding a molecule of species j, provided that we have multiple species present in the system or multiple components present in the system. So, then going back to our earlier definitions of energy, let us say if I look at my du, du was TdS minus PdV. So, we already have accounted for the temperature and entropy and pressure and volume, and clearly this energy that I am talking about, that is a change driven by addition of a molecule, is clearly not accounted for in whatever we have written so far. There must be something else coming in this picture, and that something is simply the definition of the chemical potential. So, we say that mu j is the change in the energy by adding a molecule of species j. So, let us say in total we are adding some d and j molecule, where n j is the number of molecules of species j in system. So, d and j is the change that is happening. This multiplied by mu j, that is the energy by adding one molecule in the system. So, this summed over all the species becomes the definition of change in internal energy for a multi-component system, right. Now, when we talk about, for example, enthalpy, again you will have the same change. What will change between internal energy and the enthalpy is that the other natural variables will change. Let us say for example, if I write dH, that is equal to TdS plus VdP for a one component system. So, that remains unchanged. The only difference between U and H in this case, if I exclude the chemical potential part, is that the volume as a natural variable in U is replaced by pressure as a natural variable in H, but the effect of addition of the molecule that I have added remains the same. So, this will be simply plus mu j d and j. That is to say that I can write now all of my expressions of the one component system by extending to the multi component system by simply adding sum over mu j d and j. So, you have du equal to this, dH as we discussed and dF is equal to minus S dt minus P dV for a one component system. Again we have the same term, and similarly for dG. So, now you may recall that I was telling you that chemical potential is a change in energy, and I did not say which energy is that. So, which energy is that depends on what are the other controlling variables. Let us say for example, if I am controlling temperature and pressure, in that case I will use Gibbs energy. If I am controlling temperature and volume, I will use the Helmholtz free energy. If I am controlling entropy and volume, I will use the internal energy, and so on, right. So, that particular contribution coming from the addition of the molecule of species J, that remains the same in all these cases. Now, what also happens is that earlier U was a function of S and V alone, but now U is also a function of the number of molecules in the system, because we have added a new term d Nj multiplied by mu j. Nj becomes the independent variable or the controlling variable. So, we should have ability to control the number of molecules, or we should have ability to perform experiment for different number of molecules of species J. So, I will use a curly bracket here to indicate that this is for all species in the system. So, this curly bracket indicates that we are actually doing U, S, V, N1, N2 and C for the C components that we have in the system. So, if you have 2 components, you will have N1 and N2. If you have 3, you will have N1, N2 and 3 and so on. So, whenever I use a curly bracket, it means I am writing a shortcut for all possible values of J. Similarly, here what you will have is H as a function of S, P and J, here F as a function of T, V and J, and here G as a function of T, P and Nj. Okay. So, if this idea is clear, now we are coming to the basic point of thermodynamics, that is like, although we have defined the thermodynamic functions and we have mathematically found a relation between all these functions that we have written, we have not so far said that what should be this value of energy, ultimately where the system should go towards. And what thermodynamics says that we need to minimize these energies, and when I say minimization, it means different things in different contexts. So, I am coming to the point of why do we minimize the thermodynamic functions and which thermodynamic functions we should minimize under which particular condition. So, let us get on this by using some examples. So, let us say for example, I am looking at a system that is isolated. And what do we call an isolated system? The one where the system and the surrounding does not exchange mass or energy. So, there cannot be mass exchange and there cannot be any energy expense, right. So, what this means is that when I go to the first law and we talk about energy of system plus surrounding, or to the second law when we talk about entropy of system plus surrounding, the surrounding itself is not playing any role in the isolated system case, because there is no exchange whatsoever between the mass and energy, right. So, we do not even have to worry about the entropy change in the surrounding or the energy change in the surrounding. The system itself is sufficient for the description of the system. All right. So, in this particular case, we have certain number of molecules in the system and we start with some energy, and we have said the energy is sum over the number of molecules having some energy epsilon I multiplied by the energy epsilon I, where I represents the energy levels that can be present in the system. So, you can have ground state epsilon naught, first state epsilon 1, second state epsilon 2, energies have to be discretized. There can be a maximum possible energy and there can be a minimum possible energy, and we have discussed that this Nj or Ni is given by the Boltzmann distribution at equilibrium. So, with this particular idea, now we can say that where is the tendency of system, what the system wants to do. So, we have said in the very beginning when we are doing the coin toss example that the system favors a most probable distribution, or when we discussed the exchange of quanta, we said that it should favor a most probable distribution. And what is that correspond to? It corresponds to the highest entropy. That means the entropy has a tendency to maximize, and that is also a statement of second law of thermodynamics. The only change here is that there is no surrounding whatsoever. So, in this case essentially what should happen is that S should be maximized, and that means that delta S should be higher than 0. Now, we know that my u is a function of S and V. So, therefore, I can also write S as a function of u and V, and u in this case is constant. So, I have ability to control u, and I have anyway doing a constant volume system. There is no additional work being done on the system. So, volume also we can control. So, why did I write this is because just like I wrote du as TdS minus PdV plus sum over mu j d and j, I can also write this expression by moving ds to the other side and du to the right hand side. So, what you will have is ds is du by t plus pdv by t minus mu j d and j by t. Whatever we had here was for a one component system. For a multi component system you will have u, v and j, and it is this entropy that we have to maximize. So, the problem really is maximization of the entropy, and the way we have written, we have simply replaced internal energy by the entropy as the function of interest, because mathematically I can write the expression that for du in terms of ds as well, and we have a clear sense that the entropy should be maximized. We should go towards the most probable distribution. Now, let us imagine that the system is not isolated. Let us now take a case when the system is a closed system. And what is a closed system? A closed system is where the system cannot exchange mass. So, mass exchange is not allowed, but it can exchange energy with the surrounding. So, this means I can no longer ignore the surroundings, because surroundings are exchanging energy in the system. Whether it is adding or taking away is not very important, it is exchanging energy in some particular way. So, therefore, those must be considered. So, now the first law tells me that my delta u of the system plus delta u of the surrounding should be equal to 0. Note that it was also true in the previous case, except that the delta u of system was not affected by the surrounding at all, because surrounding has no effect on the system. But in this particular case, what this means is that the energy of the system u can actually change, because the delta u of surrounding may be non-zero, or the energy of the surrounding can change. Once they exchange energy, then u is no longer constant. So, in the earlier case, when we said that I write S as a function of u and v, I had the ability to control u, because u was not changing in the system. In this case, the u in the system can change, because surrounding can add energy on the system or take energy from there. Okay? This is a very important point that comes in existence as soon as we are doing a closed system. Now, the second law tells me that delta S of system plus delta S of surrounding should be higher than 0. And then the argument of Clausius is that delta S of surrounding is the heat added to the surrounding divided by the temperature. So, what this boils down to is delta S system plus Q surrounding by T should be higher than 0 for the system. Now, I will invoke the first law again. What the first law tells me is that the change in the internal energy is given by the heat that is added and the work that is done on the system. So, the delta U system is also given by the Q and the work that is done on the system. The same thing I can write for the surrounding as well. So, now we have assumed that the system, or we can assume that the system is having a constant volume. Let us say if it is a closed container. So, in that case there is no work being done, because work we have defined as pressure multiplied by volume change. So, if I assume constant volume, then we can say that delta U of surrounding is equal to Q of surrounding, because the W is 0. So, therefore, delta U of system is minus of Q of surrounding, or Q of surrounding is minus of delta U of system. If I now put this back in this particular expression, what do I get is delta S system minus delta U of system by T should be greater than 0, and what this means is that T delta S of system minus delta U of system is higher than 0, or we can write this as simply taking a negative of this, delta U of system minus T delta S of system should be less than 0, right. So, although the entropy was being maximized when we had an isolated system, in the closed system entropy is still being maximized, but that entropy is for system plus surrounding. So, what we have managed to write is the same expression of second law of thermodynamics in terms of the energy change and the entropy change for system alone, right. And what this means is that instead of S being maximized, we can define a function u minus Ts that should be minimized. The change in u minus Ts, that is given by delta u minus T delta S, which by the way is only true when the temperature is constant. So, let us say we are able to maintain constant temperature, then the change in u minus Ts is delta u minus T delta S. Now, that change should be less than 0, unlike delta S in the previous example. So, this means U minus Ts should be minimized. And what is U minus Ts? The U minus Ts is, we have defined as the Helmholtz free energy. So, now what we have concluded is that for a closed system at constant volume, and we have assumed constant temperature as well, and at constant temperature the Helmholtz free energy should be minimized. And this is no big news, in other words, because this free energy was a natural function of temperature and volume. What this means? We should have ability to control temperature and volume. So, if I can do the experiment at constant temperature, that means I can control temperature. Similarly, if I can do experiment at constant volume, I can control the volume. So, what essentially it means is, if I am doing an experiment at constant T and V, or more correctly saying, if I can control temperature and volume, then the Helmholtz free energy should be minimized, and the minimum value will correspond to the equilibrium condition. So, equilibrium, this is the thermodynamic equilibrium at controlled temperature and volume is given by minimum of F. That tells the tendency of the process. This is the confusion that people often have, those coming from the undergrad thermodynamics background. We are told that Gibbs energy should be minimized, and we always take blindly that the Gibbs energy has to be minimized. This is not true. We need to look at what exactly is being controlled in the experiment we are doing. If the temperature and volume is being controlled, whenever we say constant T and constant V, what it means, I can do the experiment at different temperatures and different volume. So, I have ability to control temperature and volume, and in those cases the thermodynamic equilibrium is given by the minimum of the Helmholtz free energy, right. So, it really depends on the system under consideration. When we were doing isolated system, in that case it was equilibrium was given by the entropy maximum. Actually, entropy maximum is always the condition, but it is the entropy of system plus surrounding. Only in the case of isolated system, surrounding did not have any effect, and therefore, we said that we should simply maximize the entropy of the system. So, if this is clear to us, let us now do a third example and look at what we have if we have an open system. So, an open system is one in which we can not only exchange mass, but we can also exchange energy with the surrounding. And again, the approach that we follow remains the same as what we had followed earlier. Again, we assume for the argument's sake that volume is constant. So, now how do we proceed? So, we again write the first law expression, delta U system plus delta U surrounding is equal to 0. That means, delta U system is minus delta U surrounding, and delta U minus delta U surrounding is the minus Q surrounding, because again we are assuming there is no work that is being done on the system. However, we also need to add to this the energy that is added by the molecules that is present in the system now, that was not there earlier. That is coming from the exchange of molecules from the surrounding to the system. So, let us say that is sum over mu j delta n j. Keep in mind that whatever change that we have in the system for the number of molecules will be negative of the change in the surrounding, because molecules, if they come from surrounding to the system, the number of molecules in surrounding is decreasing and number of molecule in system is increasing, right. Again we had the same argument for the entropy change, delta S system plus delta S surrounding must be higher than 0, and delta S surrounding again is Q surrounding by T. However, the Q surrounding has changed now. So, Q surrounding earlier was simply minus of delta U cis, but now it also contains the term mu j delta n j. So, you have delta S system plus mu j delta n j minus delta U cis divided by T, that should be equal to greater than 0. So, therefore, we now have the condition delta U cis minus T delta S cis minus sum over mu j delta n j less than 0, which essentially boils down to saying that U minus T s minus sum over j mu j n j, this should be minimized. So, this U minus T s minus sum of mu j n j should be minimized, right. So, what we have tried to establish is the meaning of the energy that we need to minimize will change depending on the system under consideration. So, we should not really blindly taking this energy or that energy, we should try to see what is the variable that is being controlled in the problem. Are we doing experiments at controlled volume or at controlled pressure? Are we doing experiments at controlled entropy or controlled temperature? Are we doing experiments at constant number of moles or constant chemical potential? The last one we will discuss later. So, this is how we can build the appropriate thermodynamic function for that problem, and this is what we have to minimize, not Helmholtz or Gibbs or internal energy for every particular problem, because that will only have a meaning when we have certain variables being controlled. Let us say Gibbs energy only have a meaning when temperature and pressure are the controlling variable. Helmholtz energy only has a meaning when temperature and volume are being controlled. If we are doing for a case where temperature and pressure is being controlled, we should not be using the Helmholtz free energy, we should be using the Gibbs free energy. So, this is how we will choose a thermodynamic function, and this is actually completes the idea of energy that we began with. Ultimately, energy is defined as a thermodynamic function in our argument, and that thermodynamic function has to be minimized. Now, which thermodynamic function we use depend on the problem under consideration. So, before we conclude the lecture, there is one point I want to mention here, that even though we wrote this chemical potential mu j and it may appear to you as something that is constant, it is actually not a constant always, right. So, let us say for example, if I add a foreign molecule in the system and I add one molecule, then I add the next, then I add the next, then I add the next, and I keep on doing it, the chemical potential will not remain the same. because after some time, if it is being favored, you should either have more affinity for that molecule, or if it is not being favored, you should have lesser affinity, right? And this should reflect in a change in chemical potential. So, the way to think about it, let us say for example, if I start with pure water and I add 1 spoon of sugar. So, for first spoon I can easily mix it and it dissolves. When I add the second spoon, it may also dissolve, but after third, fourth or fifth spoon, it will become increasingly more and more difficult for the sugar to dissolve in water, and after a certain point the sugar will precipitate, and this happens because the chemical potential changes as the composition changes. So, keep in mind that the chemical potential is not a constant, it is a function of composition. Similarly, chemical potential is also a function of temperature and pressure. If for example, we are adding sugar in hot water, it should be easier to mix in comparison to the cold water. The same dependence may also be with the pressure, right. So, that particular argument actually drives whether you will have a mixing of two systems or whether you will have a demixing or a phase separation, and we will come to that in later part of this course. So, with that I want to conclude here. Thank you.